I think we can start.
Okay.
Perfect. Hello, everybody. Thanks for coming to this webinar. I'm Taylati Yahya from the University of Rabat. First of all, and on behalf of my colleagues in the organizing committee, I would like to thank Professor Takaaki Kajita, who accepted our invitation. It's both an honor and a privilege for us in the Refelxions think tank to bring you this program today. We have a very special guest, a distinguished Nobel Prize laureate, Professor Takaaki Kajita, who was really kind enough and accepted to share with Moroccan youth and researcher his brilliant experience and pioneering work on neutrino. This webinar will be organized as follows. After the introduction of Professor Takaaki Kajita, he will give a lecture of about 35-40 minutes. After his talk, we will collect some questions from the chat room. Please feel free to ask both in French or in English. It doesn't matter. We will take care of them. You have both chat room and the section question and response that you may use. Okay, so let me please tell you a little bit about the background of Professor Takaaki Kajita. So Professor Takaaki Kajita was born in March 1959 at Hagashima, Tsuyama in Japan. He studied first at Saitama University and then at University in Tokyo in Japan, where he got his master degree and his PhD in 1986. And since 1998, he has been at the Institute for Cosmic Ray Research. In 1999, he became professor at the University of Tokyo, and he is the director of the Institute for Cosmic Ray Research. He is a principal investigator at the Institute for the Physics and Mathematics of the Universe. He has recorded and he has received numerous prizes. He has been awarded the Asahi Prize with the Camiocande experiment, the Bruno Rossi Prize, a second Asahi Prize with Supercamiocande collaboration, the Nishino Prize, Moral Prize, the Panofsky Prize, the Yuji Totsuka Award, the Japan Academy Prize, the Fundamental Physics Prize, the Homi Bhabha Medal and Prize from India, and as you know, of course, the Nobel Prize in Physics in 2015. Professor Takaaki Kajita did his PhD in Tokyo under the direction of Professor Matoshi Koshiba. They were on Kamioka, one of the major research centers in the world. And as you know, his supervisor, Professor Koshiba, earned the Nobel Prize in 2002 for the detection of neutrino from the sun. After that, Professor Kajita explored the nature of neutrino with an expanded detector, the Supercamiocande one, and was able to resolve one of the biggest open questions in physics, which is whether the neutrino have a mass or not. He will present his work with neutrinos, this phantomatic particle, which is still full of puzzles and mystery that need to be understood. Before to give him to the floor, I just would like to mention that Morocco, and since 2011, joined this international effort to understand the properties of these phantomatic particles, neutrino, through two projects, Antares, a big neutrino telescope running in the Mediterranean Sea, and a second huge telescope KM3-NET, which is in construction, and part of this telescope will be integrated in Rabat and Oujda universities. Thank you, and the floor is yours, Professor Takaaki Kajita. I will let you share your slide, please.
Okay, thank you. Yeah. Okay, well, good morning. And thank you very much for the kind invitation, also the kind introduction to of myself. Okay, today I'm going to talk about oscillating neutrinos. Now, in this page, you see a photo. And this is Supercamiocande. So today, I'm going to talk about the neutrino studies in Supercamiocande. This is the outline of this talk. First, I'm going to briefly discuss what are neutrinos. Then, before discussing the Supercamiocande experiment, I want to briefly discuss the early days, that is the Camiocande experiment. Then discovery of neutrino oscillations, solar neutrino oscillations, future prospect, and summary. Okay, what are neutrinos? Well, neutrinos are fundamental particles like electrons and quarks. And neutrinos are something like electrons without electric charge. In fact, this feature has a profound impact to the feature of neutrinos. Neutrinos can easily pass through even the Earth, but they can interact with matter very rarely. And in fact, this is a very important feature for the neutrino astronomy, such as Antares. But today I'm going to skip this part. I'm going to talk about oscillating neutrinos today. Well, I have two more slides for introduction. Neutrinos, like the other particles, have three types or three flavors, namely electron neutrinos, muon neutrinos, and tau neutrinos. And very importantly, in the very successful standard model of particle physics, neutrinos are assumed to have no mass. However, physicists have been asking, neutrinos really have no mass. So this neutrino mass was a very important agenda in the neutrino physics for many years. Now, how can we study neutrinos? Of course, we can never see neutrinos themselves. Then, how can we study these neutrinos? And neutrinos sometimes interact with the nucleus. And in this case, charged particle is emitted. And then we have many ways to observe these charged particles. For example, in the experiment I'm going to discuss, the nucleus is a water nucleus, and therefore charged particles propagate in the water. And in this case, photons are emitted. This is called Cherenkov photons. And therefore, if we have photodetectors, we can detect these photons. And by observing these photons, we can say that charged particle propagated at that time, and that means neutrino interact at that time. So this way, we study neutrinos. Okay, now I'd like to move on to the early experiment, that is the Kamiokande experiment. Let me briefly mention the motivation for the Kamiokande experiment. In the 1970s, grand unified theories of elementary particles were proposed, and these theories predicted that protons should decay with the lifetime of about 10 to 30 years. Well, 10 to 30 years is a long lifetime, but this can be measurable. And the implication of the proton decay was so profound. Therefore, several proton decay experiments began in the early 80s, and one of them was Kamiokande. And this is the sketch of the Kamiokande experiment. So it was a big water tank in underground. It had about 16 meters in diameter and 16 meters in height. And it contained about 3,000 tons of very clean water. And if a proton in this water decay, then typically 2 to 3 charged particles are emitted, and therefore these particles emit Cherenkov photons, and these photons are detected by the photodetectors that are instrumented in the inner surface of the detector. So this way, we wanted to observe proton decays. By the way, let me introduce the location of the Kamiokande experiment. This is the map of Japan, and the location of the experiment is shown by the arrow. So you can see this experiment must be in the mountain area in Japan. And in fact, it's right. The site looked like this. This was a photo taken in the 1980s. So this photo was taken when the Kamiokande experiment was running. And in fact, the Kamiokande experiment was constructed in the mountain, in one of these mountains. And I'd like to show you this photo. This photo was taken in the spring of 1983 when we constructed the Kamiokande experiment. And you can see in the middle, there's Professor Koshiba, as introduced in the introduction. He received the Nobel Prize in Physics in 2002 based on the neutrino result in Kamiokande. In any case, these are the people who constructed the Kamiokande experiment. By the way, this is in fact the entrance to the mine. So the Kamiokande experiment was constructed in the mine. And well, let me tell you how we access to the underground. We took a mine train. This is the train we took every day. So with this train, we went underground. But basically, we went underground horizontally. Then at the underground site, it was about 1,000 meters from the top of the mountain. And there we constructed the Kamiokande experiment. And this photo shows the construction of the Kamiokande experiment. As I said, Kamiokande had 16 meters in height, and we wanted to install the photodetectors, photomultiplier tubes, onto the wall of the detector tank. And that was a big issue. And after some discussion, we finally decided to use these plastic boards to install the photomultiplier tubes onto the detector wall. Anyway, although working condition was not so great, but anyway, we were successful, and the experiment started in July 1983. And of course, we wanted to observe proton decays. And well, if the proton lifetime was 10 to 30 years, we should have been able to observe proton decays, say, every week. But unfortunately, proton lifetime was much longer than expected. Therefore, we only observed background events. These are neutrino interactions. And these neutrinos are created by cosmic ray interactions in the atmosphere. And cosmic ray particles entering into the atmosphere interact with the air nucleus, and then in these cases, typically pions are produced. And these pions are decay to other particle muon, then to electron, and during this decay chain, neutrinos are created. And these neutrinos, sometimes some of them interact in the Kamiokande detector. And these are the most serious background to the search for proton decays. And well, okay, let me talk about our study around 1986. In 1986, we still wanted to observe proton decays, but so far we didn't observe them. And therefore, in that year, we developed new software to improve the proton decay analysis. We hoped that if we improve the signal to noise ratio, maybe we can observe proton decays. Anyway, we developed a new software. Then, as usual, we have to test these new software. And as a test, the neutrino type was studied for atmospheric neutrino events so far observed in Kamiokande. The figure shown in the right side of this slide shows the event observed in Kamiokande. Here, the cylindrical detector is open to flat, and the circles show the signals each photomultiplier tube observed. And the area is proportional to the pulse height, or number of photons these photomultipliers observed. And this is the typical single chain-covering muon neutrino event. Anyway, according to this new software, anyway, we tested this new software, and we found, unexpectedly, that the number of muon neutrino events was much fewer than expected. Of course, at the time, we were testing the new software, and the software told us unexpected. Therefore, of course, we thought that there must be something wrong with the new software, or maybe some place else, some problem. Anyway, it was so clear that there must be some problem. So we started the studies to find out what is the mistake. That was the late 1986. Well, I think around that time, we had a lot of time. About a year, we continued the studies to find a mistake. But we couldn't find any serious mistake. So after about 1 year of these studies, we concluded that the mu neutrino deficit cannot be due to any major problem in the data analysis nor the simulation. And therefore, of course, we published our data. And in fact, this paper is quite simple. We simply reported the number of mu neutrino events observed in Kamiokande so far. That was about, well, I don't remember the exact number, but around 80 some number. But the simulation told us that there should be about 140 some number of mu neutrino events. So there is clear deficit. We also counted the number of electron neutrino events. And for the electron neutrino events, the data and the simulation agreed reasonably well. So that was the content of that paper, quite simple. Well, okay, the paper itself was so simple. However, the physics community had rather negative impression about this result. People thought that there must be some mistake in the data analysis. But well, of course, we were very, very careful before the publication. Therefore, we thought that the deficit of mu neutrino data must be real, and there must be some reason for that. And of course, we had no clear idea what was the cause of the deficit. But I was most excited with the data. And I enjoyed to find out the cause of the deficit. We wanted to know what was the cause. And therefore, I changed my research from proton decay searches to neutrino studies around that time. And of course, with this data alone, it is not possible to find the single unique reason for the deficit. But, sorry, no, I should mention one more thing. Well, initially, there was no other supporting data from the other experiment, but a few years later, another large water Cherenkov detector, IMB, also reported the mu neutrino deficit. So with this result from the IMB experiment, people begin to be more serious about the deficit. Anyway, as I said, with this data alone, we are unable to find the cause for the deficit. But from the beginning, we have been thinking that maybe the deficit was due to neutrino oscillations. In fact, neutrino oscillations was predicted more than 50 years ago, theoretically, by Maki, Nakagawa, Sakata, and Pontecorvo. Sorry. And well, according to the neutrino oscillation theory, if neutrinos have mass, neutrinos change their type or flavor from one type to the other. For example, mu neutrino could oscillate to mu tau, and here in this graph, I show you the probability that mu neutrino to remain mu neutrinos. So after some distance traveled, this probability goes to very low, but if they continue to travel, the probability come back to unity, go to low, come back to unity, and so on. And when the mu neutrino, the probability that mu neutrino to remain mu neutrino goes down, then the probability mu neutrino change to tau neutrinos goes up. And this is neutrino oscillations. And if this is happening, then one can easily explain the deficit of mu neutrinos. By the way, today I'm speaking to the physicists, including undergraduate and graduate course students, that if I speak to the general audience, I show this slide. So, well, according to this slide, mu neutrino is going to change to tau neutrino, then come back to mu neutrino, tau neutrino, and so on. So this is neutrino oscillations. Anyway, there could be some other possibilities to explain the mu neutrino deficit. Therefore, we wanted to get some more positive evidence that shows neutrino oscillations. And for this, we thought this way. This is the sketch of the Earth. And neutrinos are created by cosmic ray interactions in the atmosphere. Therefore, neutrinos are created in every place in the atmosphere. Therefore, some of these neutrinos are created just above the Kamiokande detector. Well, okay, the height is about 10 to 20 kilometers. Anyway, these neutrinos, after traveling 10 to 20 kilometers, come to the Kamiokande detector, and the travel distance is short. Therefore, these neutrinos may have no time to oscillate. On the other hand, neutrinos are also created in the other side of the Earth. And these neutrinos must travel long distance. Typically, these neutrinos must travel 10,000 kilometers, which could be long enough to oscillate. And if we think this way, then if the deficit is due to neutrino oscillations, we naively expect that we should observe the up versus down asymmetry of the atmospheric mu neutrinos. And in fact, in Kamiokande, we try to observe this kind of asymmetry. Well, yes, we did. We tried. We tried for many years, but unfortunately, Kamiokande 3,000-ton detector was too small. And clearly, we needed much larger detector. That was Supercamiocande. Now, I want to move on to the discovery of neutrino oscillations in Supercamiocande. Supercamiocande is a much larger version of the original Kamiokande detector. It is about 40 meters in diameter and 40 meters in height, and it contains 50,000 tons of very clean water. And the fiduciary mass for the physics analysis is approximately 20 times larger compared with the original Kamiokande detector. So, in principle, the Supercamiocande should be able to observe neutrino interactions 20 times faster than the original Kamiokande. And by the way, it is an international collaboration. At present, we have about 190 collaborators from 10 countries. And let me show you this slide. This photo was taken in the spring of 1995. In that year, we were constructing the Supercamiocande detector, or in other words, we were installing the photo detectors into the Supercamiocande detector. And this photo was taken during that time. And these many people worked together to construct the Supercamiocande detector. And by the way, I want to mention that maybe 80% of these people are Supercamiocande collaborators. So we physicists worked in underground in 1995 for almost a year. Anyway, we worked hard, and in January 96, the detector was almost ready, and this photo was taken at that time. And you can, by the way, this photo was taken from the top of the Supercamiocande tank, watching inside, and you can see the water level. So around that time, we were filling pure water into the Supercamiocande tank. And the experiment started in April 96. And the neutrino event looks like this. This is a typical mu-neutrino interaction observed in Supercamiocande. And each small circle shows the photomultiplier tube that observed the photon signal. And the size of the circle is proportional to the pulse height. And the color shows the photon detection timing. So we observe these events with the rate of about 10 events per day. And many collaborators studied these events as a team. And in fact, I think our work was very successful. And in two years, we were able to show our first major result at the Neutrino conference in '98. And this is the copy of one of the slides we showed at the conference. Of course, more than 20 years ago, we didn't have PowerPoint. So around that time, we copied our data onto a transparent plastic film and wrote down several comments onto this plastic film and projected onto the screen. Anyway, there's a reason that I show you this slide. Please look at the graph, lower graph. This is the Zinc angle distribution for mu-neutrino events. Cosine theta 1 means downgoing neutrinos, and -1 means upward-going neutrinos coming from the other side of the Earth. And black circles with the error bars shows the beta, and the hatched histogram shows the Monte Carlo prediction without neutrino oscillations. And you can see for downgoing neutrinos, the data and Monte Carlo agreed quite well. On the other hand, for upward-going neutrinos, data show approximately a factor of 2 deficit compared with the non-oscillating Monte Carlo expectation. And this can only be explained by neutrino oscillations. And therefore, Supercamiocande concluded that this dense angle distribution, together with some other supporting data, gave evidence for neutrino oscillations. Well, we presented our result at the conference for physicists. Then something unexpected happened. On June 5th, '98, President Clinton gave a talk at MIT's 98 commencement. And let me pick up the part that is relevant to the Supercamiocande experiment. He said, just yesterday in Japan, physicists announced the discovery that tiny neutrinos have mass. Now, that may not mean much to most Americans, but it may change our most fundamental theories from the nature of the smallest subatomic particles to how the universe itself works, and indeed how it expands. And of course, as the US president, he mentioned that in Supercamiocande, US physicists are also involved. Then he came back and said, the larger issue is that these kinds of findings have implications that are not limited to the laboratory. They affect the whole of society, not only our economy, but our very view of life, our understanding of our relations with others, and our place in time. So, well, I think we were really honored to hear this kind of remark from the US president on the next day of the announcement of the oscillation discovery. Okay, now let me briefly discuss the solar neutrino oscillations. Well, this is the photo of the Homestead solar neutrino experiment. And this experiment observed solar neutrinos for the first time about 50 years ago. However, the event rate was only about 1/3 of the prediction. And this problem was confirmed by the subsequent experiments in the 80s and 90s. But until this century, we didn't know what was the cause of the deficit. And the main experiment to understand this problem was the snow experiment. It was a heavy water detector located 2 kilometers extremely deep underground. And in fact, using heavy water was very important to understand the solar neutrino, to understand the cause of the solar neutrino deficit. And I'd like to show you the main result from the snow experiment, because they use heavy water, they use deuteron, and therefore neutrinos are observed in 2 different ways. Electron neutrinos interact with a deuteron, producing E- and proton plus proton. And this way, they can observe mu-E flux. Also, neutrino interact with a deuteron and disintegrating this neutron. And this is a neutral current interaction. Therefore, this interaction is not dependent on the neutrino flavor, neutrino type. So with this interaction, snow can measure the total solar neutrino flux. And then this is the snow data. If they observe electron neutrino only, the observed event rate was about 1/3 of the expectation. However, if snow observed the total neutrino flux, the event rate was as expected. So this clearly told us that 2/3 of the solar neutrinos are mu plus mu tau. And since the sun can only generate mu-E, this was the evidence for neutrino oscillations. So this was the discovery of the second neutrino oscillations. Then, because there are three types of neutrinos, we naively expect there should be the third oscillation channel. And in fact, the third oscillation channel was discovered around 2011 to 2012 by these experiments. Well, to be honest, Nova experiment came slightly late, but anyway. And these experiments observed the evidence for the third oscillation channel. So at the time, we understood the basic structure for three flavor neutrino oscillations. Okay, I mentioned that President Clinton mentioned the Supercamiocande result in his talk at MIT. But you may ask, why President Clinton was so excited with the neutrino mass? Well, of course, electrons have mass, quarks have mass. Therefore, it may be, you may think that it may be natural that neutrinos have mass. Well, in fact, we are excited with the neutrino mass. And let me tell you why we think that neutrino mass are important. Here, I show the mass of charged leptons and quarks. And let me now overlay the, now let me plot the neutrino mass into this figure. Then the neutrino mass are plotted here. So clearly, neutrino mass are much smaller than those of quarks and charged leptons. And in fact, if you are careful, you can immediately find that neutrino mass are approximately or maybe more than 10 orders of magnitude smaller than the corresponding mass of quarks and charged leptons. And we believe this is the key to better understand elementary particles and the universe. So neutrino mass is extremely small, therefore we are excited. And of course, if we understand the mechanism to generate extremely small neutrino mass, we can better understand elementary particles. But I also wrote the universe. Why universe are relevant? And well, let me again explain why we think the universe is relevant. This is, of course, the photo of the far universe. We can see many stars and galaxies. And there's one thing that we know. These stars and galaxies are made of matter. We know that there is no antimatter star or no antimatter galaxy. That seems to be too obvious. But if we think about the Big Bang universe, this may not be so obvious. In the very hot Big Bang universe, particles and antiparticles are always created simultaneously. Also, particles and antiparticles meet and disappear, annihilate, disappear. So in the very hot Big Bang universe, always matter particle and antimatter particles are created simultaneously. Therefore, in the Big Bang universe, very hot universe, we naively expect the number of matter particles and antimatter particles should have been equal. Then with the universe cool down, particles and antimatter particles meet and annihilate. Therefore, we naively expect in the present day universe, there should be no matter, no antimatter. But of course, we know that there are matter particles. Well, in a sense, we understand this problem. In the Big Bang, very hot universe, the number of matter particles were, say, 1 billion 1. But the number of antimatter particles were 1 billion. They were almost equal. Then with the universe cooled down, matter particles and antimatter particles meet and annihilate. Therefore, the 1 of 1 billion 1 remains, and this is the present day universe. Okay, so this way we understand. Of course, 1 billion 1 and 1 billion were almost equal, but not exactly. Therefore, we should be able to explain. We have to explain why there were extra 1 in the matter particle side. And in fact, we do not know. But physicists have been thinking that neutrinos with very small mass might be the key to understand the big mystery of the matter in the universe. This is just an idea. And therefore, we have to check if this idea is real or not. Unfortunately, the present day experiments are not powerful enough to answer to this question. So we have to think about the future experiments. In fact, there are 2 large projects going on. One is the Dune experiment in the United States. Another is the HyperCamiocan experiment in Japan. And with these experiments, we'd like to observe if oscillations of neutrinos and those of antineutrinos are different. If we observe the difference, it will be the first step to understand the origin of the matter in the universe. So we think these experiments are very important. And since I'm involved in the Japanese project, therefore I want to briefly mention about the next generation HyperCamiocan. First of all, I want to mention that water Cherenkov detectors have been extremely successful. Therefore, we have been thinking that the extension of the existing Supercamiocande should be the natural direction. In fact, the HyperCamiocan detector is a bigger version of the present Supercamiocande. The fiduciary mass is about 10 times larger than the present Supercamiocande's mass. And because of the huge mass, there are many important research topics in neutrino physics and neutrino astrophysics. The very important news is the construction of this detector has started in this year, and the experiment will start in 2027 or so. Anyway, this is a huge experiment, and collaboration is also large. HyperCamiocan collaboration has more than 400 members from 19 countries. And I'd like to briefly mention the sensitivity to the difference of neutrino oscillations and anti-neutrino oscillations. In other words, CP violation. And this is a sensitivity to the CP violation in the Dune experiment and HyperCamiocan experiment. And depending on the CP phase, which is shown in the horizontal axis, you can see how significantly we could observe the CP violation. And please look at the orange band for the dune case and the red curve for the hyper-K case. And both experiments are very sensitive. In the optimal case, they could reach the 7 to 8 sigma discovery. And even for the 5 sigma discovery, the phase space is more than 50% of the whole CP delta phase. So we think that both experiments have very high sensitivities. Furthermore, finally, I want to mention about the proton decays. I said the original motivation for Kamiokande was proton decay. Unfortunately, Kamiokande didn't observe proton decay. And in fact, in Supercamiocande, we continued to search for proton decays, but we didn't observe. And therefore, we'd like to continue the search for proton decays in HyperCamioCande and the next generation experiments. And this is the sensitivity of the proton decay discovery. And well, after say 20 years of the operation, HyperCamioCande discovery potential is 10 to 35 years for E plus pi 0 mode and 3 times 10 to 34 years for new K plus modes. These modes are very important decay modes of proton decays. So, and finally, maybe if we are lucky, we could observe proton decays. That is, again, very important for the fundamental physics. Okay, let me summarize. Atom-sec mu-neutrino deficit was observed by proton decay experiments unexpectedly. And subsequently, in 1998, Supercamiocande discovered neutrino oscillations, which shows that neutrinos have mass. The discovery of non-zero neutrino mass opened the window to study physics beyond the standard model of particle physics. And neutrinos with small mass might also be the key to understand the fundamental question of the universe, that is the matter in the universe. So we think that neutrino physics will continue to be very important in the future. Okay, that's all. Thank you very much.
Thank you, Professor Takaaki Kajita, for this brilliant lecture. Time, I think, to collect some questions. So please, you can feel free to ask your question both in the chat room and in the question response section. We have already one question from Rafiq El-Rabit from the Laboratory of High Energy Physics Modeling and Simulation in Rabat. He say, you have mentioned in slide 14 that the Cherenkov effect is used in the neutrino studies having place in Kamiokande experiment. However, to the best of his knowledge, the Cherenkov effect only applies to electrically charged particle. So he is a bit confused. If you don't mind, he asked, could you please elaborate how the Cherenkov effect is used in this case?
Oh, yes. Okay. Thank you very much for this question. And you are right. Cherenkov photons are only emitted by charged particles with relativistic speed if the speed of these particles exceed the speed of light in the medium. So the Cherenkov photons are emitted only in these cases, but that is okay to us.
Okay, thank you. A second question from Abdesamad Didi. He say beta decays causes neutrinos. Can the solar neutrino be from beta emitter produced on the sun core surface? And he has another question. please, is about how can explain why only the neutrino could be a Majorana neutrino.
Okay, first of all, about the neutrinos from the beta decay in the sun. Okay, well, certainly this, well, a small fraction of these neutrinos from the sun could be due to beta decay, However, with the present solar neutrino data, we can very strongly conclude that major part of the solar neutrinos are produced by the nuclear fusion processes. And because, well, nowadays we have a rather precise solar model, and these models have a very precise prediction about the solar neutrino flux. All of them are neutrinos, not anti-electron neutrinos. And from the lowest energy PP neutrinos to the high energy boron H neutrinos, we have now the measurement, and these measurements are in good agreement with the solar model if we take into account the solar neutrino oscillation effect. So we have now a very high confidence that major part of these neutrinos are produced by nuclear fusion processes. About the second question, the Majorana nature of neutrinos. In fact, this is a very important question. Neutrinos are only elementary particles that have zero electric charge. Therefore, people have been thinking that neutrino could be a Majorana particle. And in fact, because of the Majorana nature, we can easily explain, not easily, but we can explain the small neutrino mass naturally. So we think that it's very important that we prove that neutrinos are Majorana particles. And I hope in, say, 10 to 20 years, people should be able to observe the Majorana nature. And well, I think I didn't explain. Well, of course, in order to explain the Majorana nature, there is one experiment, that is the neutrinorless double beta decay. If we observe neutrinorless double beta decay, that is the evidence for Majorana nature of neutrinos. Therefore, we really want to observe neutrinorless double beta decay. Okay.
Parfait. Thanks a lot, Professor Takaaki. I have another question from Rashid Al-Mazini. He is from Academia Sinica in Taiwan. He asked about solar neutrino experiment. What are the limits from solar model prediction on future observations?
Limit on the...
He asked about the limit from solar models predictions on future observations. Yes, that's what he said.
Yeah, actually, I'm not sure what is the question. Well, certainly, there are some uncertainties in the predicted solar neutrino flux. But well, I don't know how I should answer to this question.
Okay, so maybe Rashid Al-Mazini, could you explain more? So he said how the alignment of HyperCamiocan detector will be performed and monitored done.
Alignment of the...
I think I will... I think I will give him the possibility to ask directly his question.
Yeah. Okay.
Please go ahead, Rashid. You can ask your question. Rashid Mazini. If not, I will take it again. How the alignment of HyperCamiocan detectors will be performed and how the monitor will be done. I think that's what he means.
Okay, I see. Alignment to the direction of the beam, I guess.
Yeah.
Am I right?
I think so, yeah.
Yeah. Okay. In fact, well, the beam center is away from the direction of HyperCamiocan by 2.5 degrees. In fact, this misalignment is in fact intentional. And in this way, the neutrino beam exposed to the HyperCamiocan has a peak around 600 MeV. And that is just the oscillation maximum. Therefore, most of the neutrino has the maximum oscillation effect. And that is very useful for this experiment. And the monitor of the neutrino beam is for the monitor of the neutrino beam, we have the near detector at the accelerator site. And these detectors, well, at least at present, these detectors are not water Cherenkov detector, mostly, say, tracking or conventional particle detectors. But maybe in the Hyper-K era, we may have rather near site water Cherenkov detector.
Thanks, Professor Kajita. I think we have still time to take one or two questions, if it's okay with you, Professor Kajita.
Yeah.
So, question from El Abbasi Abdrazak. He say, thank you, Professor Kajita, to have you here and great honor. Could HyperCamiocan observe proton decay predicted by grand unification theory, SU5, SUSY, and so on?
Oh, thank you. In fact, after, say, 20 years of the operation of HyperCamiocan, HyperCamiocan could observe, say, 3 sigma effect if the lifetime is 10 to 35 years. And 10 to 35 years is within the range of the prediction by the SUSY SU5. Therefore, we have finite chance to really observe proton decays. Of course, we cannot guarantee the observation, but we have chance.
Okay, excellent. There are many questions, so I will select this one. Through the oscillation phenomena, we only deduce the difference of mass, delta M square. How did we deduce that the mass of the second and third generations of neutrino is in the range, sorry, of 0.1 eV? And are there any experimental ideas that will allow us in the future to directly measure the neutrino mass?
Okay, thank you very much. In fact, the most stringent constraint on the mass of these neutrinos come from the cosmology observations. By the detailed studies, observations of the universe compared with the simulation, people get the stringent limit on the absolute neutrino mass, which is around 0.1 electron volt. So in my opinion, even in the future, cosmological studies could be the best way to constrain the absolute neutrino mass. Of course, another experiment such as the precise measurement of the beta spectrum by Catherine could also observe the constrain the absolute neutrino mass. So anyway, we have several good ways to constrain or measure the absolute neutrino mass.
Good. Another question from Professor Mohammed Shabab. He's from University of Marrakesh. So he said, thanks, Professor Kajita, this great overview on neutrino oscillations. His question is, can the teeny mass of neutrino contribute to explain dark matter?
Oh, okay, thank you. Well, of course, neutrinos have mass. Therefore, neutrinos should be a, say, small fraction of the dark matter. Unfortunately, neutrino mass are so small, therefore, they cannot be the major part of the dark matter. Well, in fact, in two ways, neutrino mass are too small. Furthermore, these small mass cannot explain the structure of the universe. Therefore, major part of the dark matter should be some other particles.
Okay, thanks a lot, Professor Kajita. Maybe one of the last question now from Khawla Yunus and from Obari. What are your expectations for the new experiment HyperCamiocan? And she thank you for this impressive lecture. And the second question, how many PMTs are installed in Camiocan? And what is the speed of processing of electronic behind?
I see. Okay. About the expectations of expectations in HyperCamiocan. Well, certainly, I think we have a very good chance to observe CP violation in neutrino oscillations within 10 years. So that is the rather optimistic. Well, no, may not be optimistic. I really hope that we can see the CP violation effect in neutrino oscillations. And the number of photomultiplier tubes used in Camiocande, original Camiocande was 1,000. In Supercamiocande, we have 11,000. And in HyperCamiocan, we are going to install at least 20,000 and hopefully 40,000. Okay?
Okay. So hope you will succeed with the discovery of CP violation, which will mean for, of course, a third Nobel Prize for the Kamioka community, I hope. So good luck. Before to conclude, Professor Takaaki Kajita, this brilliant meeting, I will just ask you, do you think that participation of country like Morocco from the Africa in this international neutrinos collaboration is important in the moment when everyone is talking about high topics like artificial intelligence and all the other hot topics?
Yes, of course. You are more than welcome to join the HyperCamiocan experiment. And we really want to collaborate with the global community.
Okay, so you think it's very important for a country even like Morocco to join?
Yes.
Thanks a lot. Allow me just one question from Professor Lulidi from the University of Rabat. So he said theoretically, the best model for neutrino mass require lepton number violation in case of Majorana neutrino. is there any way to test experimentally processes violating lepton number violation and subsequently the CISO mechanism?
CISO mechanism. Well, certainly, neutrinos double beta decay is very important towards the confirmation of the CISO mechanism, but not the observation of the neutrinos double beta decay is not the direct confirmation of the CISO mechanism. So I don't know how to confirm the CISO mechanism.
Okay, thanks a lot, Professor Takaaki Kajita. So thanks on behalf of my colleagues in this think tank reflection. We have the culture for organizing a webinar for the general public. We have been very honored, really, and hope this pandemic will leave us, I mean the COVID, and to invite you face to face to come to Morocco, inshallah, in Arabic very soon. Thanks to everyone who connected today. And I will try to say thank you in Japanese. In Arabic is shukran, Professor Takaaki. I think in Japanese it's tomo arigato gozaimasu.
Thank you.
Thanks a lot. Bye-bye, Professor Takaaki.
Okay, bye-bye.
Bye. Bye-bye.
Okay, thank you. Bye-bye.